It is my extreme pleasure and profound honor to welcome Dr. D.K. Srivastav, sir, Professor and Head Department of Electronics Engineering, BIET Jhansi. Dr. Srivastav, sir, been an immediate teacher and legendary scholar, imparting his wide experience and knowledge in the field of electronic engineering. He has done his doctoral PhD from UTU Dehradun. His area of interest includes microwave engineering, microstrips, antenna, optical communication, sensor, and has got wide research papers and journal published in all major journals. Please, sir, uh, I call upon Dr. Srivastav, sir, now to enlighten us with his wide knowledge and experience in the field of electronics. Over to you,
Okay.
sir.
Okay. Thank you, Yatinji.
Thank you.
Okay. I am audible now?
Yes, sir.
Huh. Okay. Okay. Then it is I have been given the opportunity to take the lecture in this FDP. So as Dr. Yatin told, my field is normally communication, related to communication. So I will give you the basics of communication and then concentrate on optical communication. So as I start, we everyone I think all the participants must have been the background of electronics, BTech in electronics or communication, or they are from other field also. Yeah,
All, no, so all the participants having a background of the electronics engineering only, sir.
electronics engineering.
Yes,
Okay.
sir.
Okay. So in communication, we know communication is a means of transferring the message or information from one end to other end, from source to destination. It can be direct communication also. Communication is communication if we are able to communicate our message or information to a person we want to communicate, then it is a communication. But the problem is that in direct communication, the signal which we want to transmit is normally audio signal, and the range of audio frequency is very low, and the power content in in any signal is directly related to its frequency. So low frequency signal cannot go directly to a very long distance. So when we talk of telecommunication means beyond the limitation of human capacity, then it's the technology. We have to take advantage of technology to communicate to a far distance. So the very first step for this is to raise the frequency, to increase the frequency which can carry through which we can carry our message or information. So the first step is I think you all have heard it, is modulation. With the help of modulation we are able to communicate to a long distance and send our low audio frequency to a long distance. Apart from increasing the power with the help of carrier, in modulation what happens, we take carrier, a high frequency wave, we take a high frequency wave which is called carrier, and our low frequency modulating signal, message signal, which is of low frequency, which is actually to be sent with the help of carrier. So in this what we do, we change the properties of carrier wave according to the modulating signal, according to the message signal. And then now when we change the property of carrier according to the modulating signal, now this carrier in a way carries the modulating signal, message signal, because it's some properties means a wave can be described by mainly amplitude, frequency and phase. So if we change any of these properties, uh, any of these properties of carrier wave, then these variations.
Srivastav sir. Srivastav sir.
Yes, yes.
Sir, we are unable to see the slide, sir.
हाँ, वो कुछ टेक्निकल प्रॉब्लम आ रहा है, उससे स्लाइड्स हो नहीं पा रहा है.
Okay, sir. Okay, sir.
Okay.
Anyway,
Shall,
continue, sir.
shall I continue without slides?
Yes, sir. You can try, sir. You can go ahead, sir. For that, sir. जी.
Okay, okay, okay. So where was I? Um, hmm. So the carrier now contains the message signal in the form of variations either in amplitude or frequency or phase according to the message signal. Now this carrier which is of high frequency contains the message signal. Now we have to send only this carrier which have variations according to the modulating signal. This carrier can easily go to very long distance where we receive this carrier, and we, according to the demodulation scheme, demodulation scheme, we separate out the modulating signal, message signal from the carrier. In this way, we are able to reach our carrier to a long distance. If the frequency of the carrier is varied according to the message signal, then it is called frequency modulation. If the amplitude of carrier is varied, then it is called amplitude modulation. If phase is varied, then it is called phase modulation. One more thing is that if frequency is varied, changed, frequency of carrier is changed, then phase is also changed, and if phase is changed, then automatically frequency is also changed. So if in a way we do FM, frequency modulation, then automatically there is phase modulation also. So collectively phase modulation and frequency modulation, they are collectively called angle modulation. So this was the part of analog communication, because our message signal is also analog, and carrier wave is also analog. But apart from this use that in taking the carrier of high frequency, it increases the power of the wave to reach to a long distance. There are other benefits, advantages of modulation as well. The other benefits are, for example, suppose we directly transmit our audio signals or message signals, because they are of same frequency range, then they will get intermixed. There will be interference among all the signals. So we will not be able to separate out those signals. So this modulation also provides multiplexing, because when we take carrier to modulate the analog signal, we can take different carriers for the different applications. And this way, when the carrier is different, carrier frequencies are different, then it is the carrier frequencies which are actually to be transmitted, then these frequencies are different, so there will be no interference among them, and we are able to transmit more than many signals um, at a same time, in same channel. The other advantage is antenna height. Normally, we have to take antenna height lambda by 4. So, if frequency is low, antenna wavelength will be high. So, we will have to take antenna height for low frequency, for transmission of low frequency signal, which is not practically possible. So this also solves the modulation, also solves the problem where taking the high frequency will reduce the antenna size. So these are the advantages of modulation. In this way, we are able to, mm, with the help of modulation, we are able to transmit our signal to a long distance. This was analog signal. In analog signal, if we compare amplitude modulation and frequency modulation, obviously, if we talk of quality, the frequency modulation is far better. For example, earlier when the radio signal was using amplitude modulation, we clearly differentiate the voice quality of radio and television. The voice quality of television was very clear, while the voice quality of radio was very noisy when AM was used. Because in television, for audio signal we use frequency modulation, and video signal we use amplitude modulation. So the reason for the clarity of voice in frequency modulation is that when we transmit a signal, noise is added up in the signal, mostly in the channel, in the form of amplitude. When noise is added up in the signal, the amplitude of the signal changes. So in amplitude modulation, what happens? The variation is in the form of amplitude, and when noise will add, those variation will get changed. Will get changed, and it is changing at every instant of time. So we cannot take care of by filtering or other methods. We cannot bring it to the original value, because at every instant variation is changing, and noise changes those amplitude values. So it cannot be, so it is said, the noise once stuck in the amplitude modulation cannot be removed. While in FM, the message is coded in the form of variation in frequency. So if amplitude is changed, amplitude of carrier is changed due to noise, then it will not change the variation, because variation is in the form of frequency, and amplitude also, V max and V mean of carrier is fixed, so we can bring it to the original value by filtering it. So to a large extent, we can get rid of noise in frequency modulation, but it is not possible in amplitude modulation. Then we talk of digital modulation. In digital modulation, we take message signal in the form of pulses. Message signal is in the form of pulses, and carrier is obviously in analog signal. So the message is in the form of pulses, means it is either 0 or 1. So what happens? We do keying. Keying means the keying has two options: either lock is closed or open. So one bit 0 indicates open, and one bit indicates closed. This way, this modulation is called keying. So in keying, we again, every wave has three properties: frequency, amplitude, and modulation. If we do keying in the form of frequency, it is called frequency keying. If it is done in form of phase, then it is called phase keying, BPSK. Phase shift keying, it is called phase shift keying. And amplitude shift keying, ASK, FSK, frequency shift keying. If frequency is changed, frequency. So for example, I explain you the example with the example of BPSK, binary phase shift keying. In this, what happens, we have signal in the form of 0 and 1. So suppose we have carrier in the corresponding to bit 0, we made make no change in the carrier. And for bit 1, we change the phase of the carrier by 180 degree. So now the property of carrier is changed, that corresponding to the bit 0, there is phase shift of 0. And for the bit 1 there is phase shift of 180 degree. And this way, the carrier is coded according to the uh, pulse message signal, which is in the form of pulses, digital form, which is in the digital form. So now this the by decoding the shifts of phase shift of carrier, we can decode our message signal at the destination end. So again, the advantage of this system is again the quality, because the phase of carrier is changed. There is no change in the amplitude, and if noise is added up, it will add up in the form of amplitude. And again, with the help of filtering, we can bring the amplitude to the original form, and uh, this way, we can get rid of noise to a large extent as compared to analog modulation or amplitude modulation. So this was the basic concepts of communication system. Now I will switch over to the optical communication, because optical communication, the communication, different types of communication systems we know. Optical communication is the most efficient communication system, because its efficiency is good. It has very uh, low noise as compared to the other communication systems, because this is a guided communication media. In this, the signal which actually travels from one end to other end is optical signal. As the name suggests, it is the optical signal which travels in the optical fiber. Optical fiber guides the optical signal. Optical signal do not travel in the air. It travels in the optical fiber, so it is guided, it is trapped in the optical fiber, so it can go to a very long distance without very less attenuation or losses. The benefits of optical signal is that it is most reliable, efficiency is very high as compared to other communication systems. It since the signal is optical which travels, so it do not have EMI, electromagnetic interferences from the other signals. And then the optical fibers are made up of silica oxides, which are very abundantly present in the environment. So the cost of installing the cost of optical fibers are very low. It is very light in weight. It has very long life. It needs very less maintenance. It needs no thermal stabilization. These are the benefits of the optical communication system. So where it comes the for those applications which require high reliability, high efficiency, we go for optical communication systems. Again, as every communication system have mainly three blocks, three main components. What are those main components? First one is transmitter. Second one is channel. It can be unguided media or guided media. Unguided media means air, through air, or guided media means telephone wire, optical fiber, or anything. And other one is last one is destination transfer receiver, where we receive the signal. So in optical communication system, also we have these three parts: transmitter, then channel will be optical fiber, and then receiver. In transmitter, apart from conventional part means the first part is the device which will pick up the signal. For example, we take audio signal, then we need to have a speaker which will convert our voice to electrical signal. Microphone, sorry. We will need to have microphone which will convert the sound signal to electrical signal. Now in this optical communication, this we need a device which will convert the electrical signal, this electrical signal which was converted from audio signal to corresponding optical signal, and this optical signal will travel through optical fiber. Then again at receiving end, we the first device we require is the photodiode. It is also called photodetector, which will detect the light. As the name suggests, photo means light, detector means which will detect it. So we need a device which will detect this light, which has been transmitted through optical fiber to receiver. Then this light will be converted to corresponding electrical signal. And then again, as in conventional system, at the end, we need a speaker which will convert this electrical signal into audio signal, which we are able to understand. The audio signal which was picked up for transmission is the actual which we will understand. So in this way, in optical communication, in the transmitter, apart from conventional system, we need a device which will convert the electrical signal to optical signal, and these devices are called light sources, and then the optical fiber, and in the receiving end, the first device we need photodetector. In optical sources, now there are requirements for optical sources also, optical fiber also, and optical detector, photodetectors also, to be efficiently used for the purpose of optical communication. Those requirements are: first of all, these three devices should be compatible. Compatible means the dimension, physical dimension should be compatible. For example, if we talk of fiber, the radius or diameter of fiber is very small. So we need to have optical source which will emit the light through such a small portion, concentrated light through such a small portion, so that it can be penetrated to the optical fiber. Similarly, the light emitting from the optical fiber, it is emerging from a very low size diameter, so it should be able to be exposed. The active area of photodetector should also be of similar size. And it should be compatible in other parameters also, because efficiency of a system, if a system consists of many components, then efficiency of system depends on every components. For example, if we talk of speed, response speed, suppose optical source is very high speed component, optical fiber also support it, and if photo detector is of slow speed, then the speed of whole system will go down. So in every respect, be we talk of efficiency, be we talk of response speed or any parameters, it should be compatible. For example, if we talk of cost, suppose optical fiber is cheaper, optical photo detector is cheaper, but if optical source is costly, the cost of overall system will go high. So it should be compatible in other respects also. If we talk of life, as I told you, the life of optical fiber is very high, very long life. So we should have optical source of very long life, and we should have a photo detector also of very long life. So keeping in mind these parameters, the optical sources which are suitable for the optical fiber communication, they are normally two types of sources. They are normally LED, as we all know, light emitting diode, and other one is laser diode. Laser, we all know light amplification by stimulated emission and radiation. These two sources are normally used in the optical fiber communication. Now, if we talk of LED and laser diode, then they are reversed to each other. In all respect, they are reversed to each other. The in LED, the advantages of LED are disadvantages of laser diode, and advantages of laser diode are disadvantages of LED. For example, first we talk of LED. You all know about LED. LED, the advantages of LED are it is very cheaper, very light in weight, very small in size. It requires no thermal stabilization. It is of very long life. It requires no maintenance. It is very rough and tough device. It needs no maintenance at all. These are the some of the advantages of LED. And these advantages are not available in laser diode. In laser diode, it needs thermal stabilization. It is very bulky. It needs maintenance time to time. It is very costly. These are its disadvantages. Means the properties which are advantageous in LED are disadvantageous in laser diode. But the technical properties which we are most interested in are advantageous in laser diode, and they are disadvantageous in LED. For example, the spectral width of LED is very wide, while the light emitting out of laser diode is highly monochromatic, highly directional, and is very powerful, and it can go to very long distance directly without much attenuation. While the output beam of LED is not so powerful, its spectral width is also very large, so it cannot be used for the beam of LED is cannot be used in step index fibers. I will explain you what are step index and other one is graded index. So the output beam of LED is normally used in graded index fiber because the core diameter of fiber of graded index fiber is more than the step index fiber. In a step index, core diameter is very less as compared to graded index. So, and one more thing that the output beam of the normal structure of LED cannot be used in optical communications. So we have a special structure which is called double heterogyne junction structure of LED, and this structure can be this structured LED can be used in optical fibers, because this is a special structure of LED which increases the efficiency of output beam. The efficiency is increased because the active area where EHP, electron hole pair, recombines and emits the light, um, are sandwiched in two layers. In two layers, that's why it is called double heterogeneous junction. And the function of these two layers are dual function. They have dual function. They have the function of carrier confinement and optical confinement, because they confine the carriers also. Carriers means electrons and holes, because if electrons and holes uh, are not lost, then if we have maximum number of carriers and holes, then the maximum number of recombination will be possible. So carrier confinement have to be attained. And then after the combination, when we get optical signal, then those optical signals should be also be confined. Their loss should be avoided, so that we can get maximum uh, output power beam. In this way, we are able to receive the powerful beam from LED. In laser diode, we know in laser diode, the principle of operation, we have normally three principle. Uh, we know absorption, spontaneous emission, and stimulated emission. Absorption is when we all know that electrons or carriers reside, free carriers are in ground state. But when they are excited, when light is impinged on the active material, then these carriers absorb the light and are excited to higher energy levels, higher energy states. But the electrons residing in higher energy state is not a normal position of an atom. It has the tendency to immediately rush to the ground state. So the when an electron absorbs the light, absorbs the heat, then it goes to higher energy state, but it immediately rushes to the ground state, and thereby emitting the light. This emission of light is spontaneous. That is why it is called spontaneous emission, and it has no relation with the input beam which was impinged on the material. It has no combination, no comparison of direction. It can be in any direction, it can be of any phase. So it is a very random emission, and this type of emission is of no use. So what we do is we make a forced emission, stimulated emission, which is called stimulated emission. And this what we do when electrons are already in higher energy state, we impinge light on the material so that the electrons from higher energy state rushes to the ground state, thereby emitting the light. Now, this emission of light, this light beam is of the same direction of the input light which was impinged on the material, and of the same phase. So, when all the beams are in the same direction, so it is very obvious that this emission is very powerful, because it is concentrated in a particular direction. It is in the same phase. It is of the single frequency. It is monochromatic beam. It is very powerful beam, which is very, very, very advantageous. So this can be used for this purpose. optical fiber communication purpose. Now, for this stimulated emission, what we should have the requirement is that the number of electrons in the excited state should be more than the ground state so that we can make stimulated emission. So this condition is called population inversion, because in general population of electrons, number of electrons in ground state are more than the number of electrons in the excited state. But we have to achieve the reverse situation of the normal state, that is the population of electrons should be more in the excited state than in the ground state, so that we can achieve stimulated emission. And this situation is called population inversion. So we need to have population inversion, and population inversion is achieved with the help of different types of pumping techniques. Different lasers use different type of pumping techniques. The pumping technique is a technique by which we raise the electrons to the higher energy state. So this was about laser diode. This was all about laser diode, and with the help of this, we are able to uh, transmit the signal through fiber to a long distance. Now we come to fiber. As I told you, fiber is normally made up of silica oxide. Silica oxide is abundantly present in our environment. So the cost of installing the silica oxide fiber, making fiber, manufacture of fiber is not very high. But again, we have some requirements for in the fiber to be used for the purpose of optical fiber communication. The requirements are that we should be able to draw long, thin, flexible wires from this material. Long means obviously we have to make a use it for the telecommunication. So we need long fibers. Then it should be flexible, because if we install it, then it should not break due to the environmental conditions, like there is it is very hot in summers, very cool in winters. So it should be able to accept these conditions and should not get broken in these conditions. And then it is of very small diameter, core is very small diameter, so we should be able to draw such a thin fibers from these oxides, from the materials which is available in the environment. These are the requirements. And above all, the very important requirement is that we should be able to make core and clad from these materials. Core and clad, what is core and what is clad? If we see the structure of fiber, in center, the most important part is called core. It is also made up of silica oxide, and light is actually trapped in the core and it travels in the core. Then surrounding the core, there is again a transparent material which is also made from silica oxide, and the function of this clad is to let the light trap in the core. It should not allow to light emerge from the core. And then these two, core and clad, are the important part of the fiber. And then after this, there are certain layers of plastic layers. They are to avoid it from the environment conditions or hazards, like stone. If stone falls on the fiber, so if it directly falls on the clad, then it will be destroyed. So there are certain layers of the plastic, so as to avoid it from the environmental temperature conditions and hazardous conditions or accidental conditions. Now, core is also made of silica oxide, clad is also made of silica oxide. Then what is the difference between the two and what is the function? Function, I told you, the light actually travels in the core and clad supports it, supports to let the light travel in the core. Then how is the difference material wise or otherwise? The difference is of they are of same material, but the difference is of refractive index. Because to trap the light in the core, we have to attain the condition of total internal reflection. And total internal reflection is possible when a light uh, light have to travel to one medium, and from the boundary of one medium and other medium, the boundary of two mediums, it will be reflected back. So for making the other medium, we need clad. So core and clad are of same material, but they have different refractive indices, and the refractive index of core is more than the refractive index of the clad. Not so much difference. They are nearly in the same range, but the refractive index of core is more than the refractive index of the clad. Now the problem is that how to vary the refractive indices of the two materials which are made from the same material. So this is done by doping the impurities. Where there are several impurities, when they get mixed up in the silica oxide, they increases the refractive index of the material. There are several materials which decreases the refractive index of the material. These materials are boron oxide, phosphorus oxide, fluorine, and some others. So some increases the refractive index and some decreases the refractive index. In this way, we are able to make core and clad from the same material silica oxide by doping the impurity in this material, and we make core and clad, and the light when it enters in the core, it interferes the boundary, and in the boundary, their boundary is separated by the two refractive indices. Then when we follow the Snell's law, we achieve the condition of total internal reflection. So light is totally reflected in the um, core, and this way, in a way, it is trapped in the core. It is trapped in the core and is able to travel to a long distance without much losses. But much losses. But we cannot say free of losses. No system can be ideal. Every system has limitation. Likewise, the optical communication also suffers some losses of the signal. These losses are called attenuation. In fact, there are two types of signal degradation. We can say the word, we can use signal degradation. This degradation consists of two types. One is loss, signal loss. Signal is lost after certain distance, which is also called fiber loss or attenuation or signal loss. Since after a certain distance signal is lost, so it determines attenuation determines the maximum repeaterless transmission distance between the transmitter and receiver, because after that distance, after that maximum distance, we are not able to properly receive the signal, and we have to amplify the signal before further transmission. And this amplifier is also called repeater. That's why it is called, it is defined repeaterless distance. The other one is the other factor responsible for signal degradation is dispersion, because light is also here travels in the form of pulses, and after a certain distance the pulse amplitude of pulse decreases, and width of the pulse increases. Okay, so suppose there are two neighboring pulses. When after certain distance their width will be increased. So after a certain distance, though it will these two neighboring pulses will start overlapping, and after certain distance, this overlapping due to this overlapping, the two pulses will be so intermixed that it will not be able to separate them out even if we receive them. And if we are not able to separate out, that means we are not able to decode the message which we actually require, which we actually want. So due to the dispersion of pulses, we are not able to decode the information content from those pulses, from those signals. So this puts the limits on information carrying capacity of the signal of the system. Even though we are able to receive the pulses, we are able to receive the signal, we are not able to decode the information. That's why it puts the limits on the information carrying capacity of the system. So these two factors are responsible for signal degradation, which puts the limits on its efficiency. The regions for attenuation, there are certain regions for attenuation. Attenuation means signal loss, or it is also called fiber loss. The first one is absorption. The other one is scattering, and the third one is bending loss or radiative losses. The absorption is the fiber material itself, or the impurity materials, impurity which were doped for making core and clad, the impurity materials, or the other impurity materials which are automatically installed in the fiber during the manufacturing of the fibers, like different type of oxides, hydroxides, and other oxides. These materials, they have tendency to absorb the light. They absorb the light. So there are two types of absorption: intrinsic absorption and extrinsic absorption. Intrinsic absorption is by the constituent absorption of light by the constituent material of the fiber, and extrinsic absorption is by the external materials like doping materials or impurities which are present in the optical fibers. They also absorb the light and are responsible for the losses of the signal. The scattering losses is that we all know the silica oxide. This is a glass structure. This is a type of glass. We know there are two types of solids, crystalline and amorphous. We know glass is a amorphous structure. Crystalline structures are those structures which have regular and refined structure of atoms distributed throughout the material, while in amorphous structures there are cluster of atoms. Somewhere there are cluster of atoms, somewhere there are no atoms available. So when a light, it is very analogous to the flow of water through a tap, through a pipe. For example, if we put obstacle in the path of water, the water will scattered out from that, and it will distribute to other sides. Similarly, when light travels in the optical fiber, when it will uh, it will mix with this cluster of atoms. The light will be scattered out, and it will follow the similar behavior, relay scattering behavior. And due to this, the light, some portion of light will be scattered out of the optical fibers and will be responsible for the losses. Third one is radiative loss due to the bands. We know we have to install fiber from uh, to a very long distance. For example, if we are installing from one city to another city, or to 50 kilometer or 100 kilometer or 10 kilometer, so it is very obvious that such a long distance cannot be a cannot be a straight path, and we all know that light travels in a straight line. So when we it will bend, though it will look like straight, but it will not be actually straight. It will have a bend, and the radius of curvature of this bend will be very high. So this is called macro bend. And there is also micro bands also, which is also responsible for radiative losses. Micro bands will be due to the during the manufacturing of fiber, because when the fiber is manufactured, the core axis is not very straight. Though from naked eyes it will look like straight, but when we look it through microscope, then it will have many bends which are so micro, so small, that it will not be visible through naked eyes, and so it do not have much contribution in the losses. It will not give much losses, but some losses will be come from this micro bands also. The major losses will come from micro bands. So in micro bands, what happens that when we will have micro bend, then the fiber is bending, then the when light and light pulse when travels in the fiber, 80% of this fiber is traveled in the uh, core, and 20% of its portion, which is also called pulse tail, is traveled in the cladding. So when the fiber gets bent, then the distance from one point to other point, when we see the distance from one point to other point, the upper portion of clad will have slightly more distance, and due to bend, and core will have slightly less distance. Then this pulse tail, which is in the core, upper portion of core, will have to travel slightly more distance, so it loses the mm, portion of light which is traveling in core, and so losses occurs due to bend. So these are the losses, major losses which are responsible for the attenuation in the fiber, and it puts the limit on distance. So after certain distance, we have to use amplifier or repeater so that it can further go to a long distance. The next one was dispersion. There are two types of dispersion: waveguide dispersion and material dispersion. Actually, what happens, there is group velocity, one factor called group velocity, in which all the modes of the light travel from a source to destination. But due to the material property, material and waveguide property, it depends on there is one factor. It depends, due to this, the different modes travel with different speed, uh, different speed. So the reaching time of all the modes at destination is not same. Hello, hello, I am audible.
Yes, sir, you're audible, sir.
Okay. So reaching time of all the modes are not same. It is slightly different. So the pulse which was concentrated at source is not now not concentrated, but it's with his we obtain pulse with pulse with his widens and amplitude reduces. And after a certain time, due to the widening of the pulses, the pulses overlap, neighboring pulses overlap, and after a certain point, even if we are able to receive the pulses, but we cannot separate them out and we cannot decode the information content from these pulses. So this is responsible for information contents, and which is also important because for the successful communication it is not important that we are able to receive the signal. It is also important that signal should be in the form that we should be able to separate out the information or message from that signal. So our signal should be in that form. So it also puts the limit. But if we compare all these parameters and efficiency of this system with other systems, it is far efficient from other systems. The other point was photo detector. And the other component, important component, was photo detector. When the signal travels from fiber, optical signal is traveling in the optical fiber. So at the receiving end, we require the device which will sense this light. Sensing the light means it will convert this light into electrical signal, which will have the information content in itself. So photo detector is that device. When light falls on the photo detector, the analogous electrical signal is obtained in the output. This output, which is in electrical form, contains the content of the light signal related to message signal. Uh, Meeting out the requirements of optical signal, as I told you earlier, the two popular photo detectors are available, which can be used in optical signal. Meeting out all the requirements are pin photodiode and APD, avalanche photodiode. Pin photodiode and avalanche photodiode. As the name suggests, pin photodiode is made up of three layers: P-type, I, intrinsic layer, and N-type. It is in the intrinsic layer where the light falls, and when this light falls, it breaks the covalent bonds, and this covalent bonds releases the EHP, electron hole pair. The diode is reversely biased, so the electrons and holes are separated out and are received at the output circuit. And in the output circuit, when these electrons or holes flows, we know the flow of electron is called current. It's called current. But the flow of electrons due to this light, because light is responsible for this flow of electrons, because when this light falls on the intrinsic layer, then only electrons are generated, electron and hole pair is created, and electrons are generated, and these electrons are flowing in the output circuit, creating the current. So this current is called photo current because it is due to the फोटो लाइट की वजह से हमें मिली है ये करंट. तो दिस इज कॉल्ड फोटो करंट एंड दिस करंट इज व्हाट वी रिक्वायर. Similarly, as was in the source, in this also the efficiency of this photocurrent is not very high to drive the output further output circuits like speaker and other things. So we need to increase the efficiency of this devices. The efficiency of APD, avalanche photodiode, is much higher than the pin photodiode, and further to increase the efficiency of APD, avalanche photodiode, we use a special structure of APD called RAPD, reach through avalanche photodiode, which multiplies the photocurrent to many times due to avalanche phenomena, and we get very sufficient powerful photocurrent which can drive the other circuits further, other circuits efficiently. In this way, we get the analogous electric current, and as was used in our conventional systems, with the help of this output electrical signal, we are able to drive the speaker or other systems, which will convert this signal into the form which we are able to understand. And in this way, the signal which we needed to transmit, we are able to receive it after the transmission. So this was the brief overview of optical communication. Yaten sir. Yaten sir, are you able to listen me?
I am here, sir.
Uh, this was brief overview. I gave it.
Yeah. Yes, sir. Hello.
Yes,
Any
yes.
questions from the participants?
Huh.
Any question from the participants? Okay, sir. So it was a nice talk with you, sir. You have discussed about the optical fiber grading issues. Even you have also discussed about inter-symbol interference also, and the banding losses also, sir. It was a good one, sir, and I hope so. It will be beneficial for the both the MTech students also and for the PhD students who are working on the optical fiber grading, sir.
Okay.
Yes.
Thank you.
And one more thing, sir, I would like to ask you, sir. You have discussed about the inter-symbol interference, sir. Hello,
Yes, yes, yes.
sir. Could you please go through that for a minute, sir? Uh,
And inter-symbol interference, actually,
there was a
people
question from
not
the
working
one of
on.
the participants. He was asking about the inter-symbol interference, sir.
That is what I explained. Na? Inter-symbol
Yes, sir.
interference means two symbols which are the two neighboring symbols. When due to the pulse broadening, due to the material dispersion and waveguide dispersion, pulse broadening occurs. And when pulse broadening occurs, मतलब पल्स का फैलाव होगा, उसका एम्पलीट्यूड घटता जाएगा और उसकी विड्थ जो है फैलती जाएगी। तो जो दो नेबरिंग पल्सेज हैं वो धीरे धीरे उनमें ओवरलैपिंग बढ़ेगी। एक सर्टेन डिस्टेंस के बाद वो ओवरलैपिंग इतनी ज्यादा हो जाएगी कि उनको हम सेपरेट आउट नहीं कर पाएंगे और उनमें इंटरफियरेंस होगा। यही कहलाता है इंटर सिंबल इंटरफियरेंस, दो सिंबल के बीच में इंटरफियरेंस।
And so you have
हेलो।
also discussed about that the materials that we are using the optical fiber, sir.
या
Sir, please, I would like to please repeat that also, sir. One of the participant was also asking to go ahead with that, sir. Once again, sir.
हाँ, उसमें ऐसा है कि हमें दो मटेरियल चाहिए कोर और क्लैड के लिए, जो कि मीडियम वन और मीडियम टू बना सकें, ताकि उनकी बाउंड्री पे जब हमारी लाइट वेव टकराए तो हम स्नेल्स लॉ को इम्प्लीमेंट करके टोटल इंटरनल रिफ्लेक्शन की कंडीशन अचीव कर सकें। क्योंकि लाइट को कोर में ट्रैप करने के लिए हमें टोटल इंटरनल रिफ्लेक्शन की कंडीशन अचीव करनी पड़ेगी। वो कंडीशन तभी अचीव होगी जब हमारी लाइट उस बाउंड्री पे टकरा के वापस रिफ्लेक्ट होगी। ठीक है।
Yes.
तो उसके लिए हमें कोर और क्लैड चाहिए जो सेम मटेरियल के हों, उनके रिफ्रैक्टिव इंडेक्स भी नॉर्मली सेम रेंज के हों, लेकिन फिर भी उनमें डिफरेंस हो। तो ऐसा करने के लिए जो हमारा सिलिका ऑक्साइड है, जिससे कोर भी बनता है, कोर और क्लैड के ये प्राइम मटेरियल्स हैं, कोर और क्लैड इसी से बनते हैं, लेकिन इसमें हम बोरॉन, इसमें कुछ इम्प्योरिटीज ऐड करते हैं। कुछ इम्प्योरिटीज ऐड करने पे इनका रिफ्लेक्टिव इंडेक्स इंक्रीज कर जाता है, कुछ इम्प्योरिटीज ऐड करने पे इनका रिफ्रैक्टिव इंडेक्स डिक्रीज कर जाता है। जो जैसे कि जो इम्प्योरिटीज हम ऐड कर पाते हैं वो फास्फोरस ऑक्साइड है, बोरॉन ऑक्साइड है, फ्लोरीन है, और एक और कोई मटेरियल है। तो इनमें से कुछ को ऐड करने से रिफ्रैक्टिव इंडेक्स डिक्रीज होता है, वो क्लैडिंग के लिए यूज हो जाते हैं। और कुछ इम्प्योरिटीज ऐड करने पे रिफ्रैक्टिव इंडेक्स इंक्रीज होता है, वो कोर के लिए यूज हो जाते हैं।
Okay. Yes, Kunja ma'am, would you like to ask some question, ma'am?
Yes, sir.
Yes,
Please
please, ma'am.
elaborate the May scattering and Rayleigh scattering.
In this fiber, we only have Rayleigh type of scattering, the scattering which is responsible for the blue color in the sky.
Any more questions from the participants? Any more questions? Okay, sir. Thank you, sir, for that, sir. It was a nice talk with you and nice discussion.